Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be talking about section 11.8, which is the concept of power series. Up to this point, we've been talking about a lot of different series and how to identify whether they are convergent or divergent. So a lot of people tend to then ask, okay, where is this going? Why are we talking about a lot of series when we've been working with a lot of integrals up to this point? And we've been doing integrals, derivatives, we even did some div-eqs, we did some differential equations. So where does this tie in? And where it ties in is the discussion of power series. With a power series, we're going to then ask the question, okay, what if we introduce another variable to this? What if we introduce a variable such as x to this situation? For example, here I have a sum of sine of nx divided by n squared. And if you start to progressively plug in values for n, what you get is sine over 1, sine of 2x over 4, sine of 3x over 9, etc. You get this almost polynomial. You get this summation of a lot of terms that are defined by x. Therefore, what you're doing is now you're defining a function based on a variable on the Cartesian plane. And then our question is, okay, what is this function doing? What does this look like? Is this getting closer to something that's more familiar as an overall function? And what happens for different values of x? Say if I plug in the value of 1, does this actually converge to something? Or what if I plug in a value of pi halves? Does this diverge to something? That's the question here. What exactly happens when we plug in different values of x? That'll be our overall question. And we'll start to deal with this a lot near the end here of chapter 11. But first, we're going to be talking about the more basic versions of these, which are going to be called power series. A power series is going to be similar to this. Instead, what you're going to have is a summation of a bunch of constant terms multiplied by x taken to some power. That power of x being the reason why we call it a power series. What you get then is a direct polynomial, but you get a polynomial of technically infinite amount of terms. Constant plus a constant times x to the 1 power plus a constant times x to the 2nd power plus a constant times x to the 3rd power, etc., etc., etc. You get all of these terms. And as we're going to show moving forward, particularly in 11.9, 10, and on, is that this is actually going to help us define other familiar functions. For example, we can take functions such as e to the x, or tangent of x, or cosine of x, or arctangent of x, or natural log. We're going to be able to define it as a series of polynomial functions. That's really helpful for us when we're applying things like integrals and derivatives, because we can take an integral and a derivative of a polynomial rather easily. However, it's a lot harder to take an integral of some very specific functions. As we've shown in Chapter 7, a lot of the times for specific functions, we have to do a completely different method, but there are still some times that we cannot solve it with what tools we have already. So this is going to allow us to take a function, such as tangent or something, and replace it with a polynomial, and then hopefully we can evaluate that new integral or that new derivative. It's also very, very good for differential equations. Now, whether these constants are the same or different, this is implying that they're different for c sub 0, c sub 1, c sub 2. If you consider them all the same, what this looks like is a pretty familiar series. If you just have a constant or constant coefficient of c, then you have c plus cx squared plus cx to the 3rd plus cx to the 4th, etc., etc. This looks a lot like the geometric series, where you have a constant multiplying by something taken to a power of n minus 1. The only reason that we have n instead of n minus 1 is because we're starting at a different place. We're starting at 0 instead of 1, but it's the overall same thing. And as we know for a geometric series for this situation of cx to the n, we know that this is going to be convergent so long as whatever value of x is, as long as x is less than 1. Specifically the absolute value of x. The absolute value of x is less than 1, we know that this converges, and it converges to c divided by 1 over x, 1 minus x. Note that now we've defined that this summation of a bunch of these terms is equal to c over 1 minus x. So we can take this function, if we define this as a function of x, we can take that and rewrite it as a polynomial of a bunch of other terms. That's the benefit there. Now, hopefully you see that for a constant term that it applies to the geometric series. However, whether you have a constant coefficient or not, you can also apply the ratio test as well. The ratio test works because you could take a ratio of functions, and we see x to the n power. That's one of our keys to maybe think about ratio tests anyway. And if you take a ratio of successive values in the series, what you end up with is cx to the n plus 1 over c to the x. And then a lot of these cancel out, and all you're left with is one value of x on top, where the c's cancel as well. And this limit, we know for the ratio test defines that whatever value that limit is, as long as the limit is less than 1, then it is convergent. If it is greater than 1, it diverges. This less than or equal 1 is what we're going to call the convergence set. At least that's what it is going to be at a base. What we're also going to do is test the values for, say, what if it equals 1 or what if it equals negative 1. And we'll call those the bounds of the convergence set. Sometimes we'll find that it converges under those specific conditions. Sometimes we find it diverges under those. But we're going to need to test those as well. Because the ratio test has the weakness that if you have it equal to 1, then it's inconclusive. So we need something else to test. But that's what a power series is in a nutshell. And overall, we're going to solve them using the ratio test. That is going to be our bread and butter here, which is nice because that's a pretty easy test to run through. So let's go through a couple examples of power series. Example 1, for what values of x does the following series converge? Note that this is x to the n over n factorial. This may look different than what we had before, but the main thing you want to focus on to recognize it as a power series is the fact that you see x to the n power. That makes it a power series. Since this is a power series, what we want to do is evaluate this as a limit, and we're going to do the limit of successive terms because we're going to do the ratio test here. This one is pretty nice. We've actually probably even done this before. If we do the limit as n approaches infinity of a sub n plus 1 times the reciprocal of a sub n, what we're going to get if we plug in n plus 1, we get x to the n plus 1 divided by n plus 1 factorial times the reciprocal of that, which is n factorial over x to the n. We rearrange some of these terms together, so we move the x's together and the factorials together. We have x to the n plus 1 divided by x to the n. And we have n factorial divided by n plus 1 factorial. Note that I'm keeping the absolute value as I go through this. The reason that that is important to consider is because we don't know what value x is. X could be positive or negative, and that can influence what's going on here. However, overall, what you get from this, x to the n plus 1 divided by x to the n, that's going to cancel out all values of x except for to the 1 power. This is going to equal x. Whereas n factorial over n plus 1 factorial, that will cancel out all terms of n except for n plus 1 on the bottom, so this will be 1 over n plus 1. So overall, we have the limits of x over n plus 1 as our limit. And we know there is still a value of n. We know that as n approaches infinity, this is approaching the absolute value of x divided by infinity, which is 0. Now, that limit equals 0, which is less than 1. And since it's less than 1, we know it converges. And note that this doesn't matter what values of x there are. X could be a value of 2. 2 over infinity still goes to 0. X could be a value of 87. 87 over infinity still goes to 0. Or it could be negative. Negative 20 over infinity still goes to 0. So we would then say that this is convergent for all values of n, or for all values of x, because it's completely irrelevant. So we simply will write that down. So we'll say that by the ratio test, this is convergent for all real numbers of x. X could be any real number, and this would still be convergent. Note that real number does not include infinity or negative infinity because those are not numbers. So overall, what we're saying is any value of x would still make this convergent. But that's not necessarily always going to be the case. A lot of the times, it's going to be a little more specific than that. Let's see an example there. Say we have the sum of n factorial times x minus 1 to the n power. Now, if you're curious about or you're concerned about this starting at 0 and having 0 factorial is 1. So that's not a problem. If you aren't aware of that, 0 factorial is equal to 1. Now, we're still going to recognize this as a power series because we have a value of x to the n power. The fact that x is a little bit more complicated is not exactly relevant. So we're still going to analyze this as a power series, and we're going to work with the ratio test to determine convergence. So here we have the limit of a sub n plus 1, so we'll have n plus 1 factorial times x minus 1 to the n plus 1 power. And we're going to divide that by the original n factorial times x minus 1 to the n power. With this, a lot of terms will cancel out. The x minus 1 to the n power will cancel out up to n. So we'll have just x minus 1 left over. And likewise, n plus 1 factorial and n factorial, this just becomes n plus 1. So we have the limit as n approaches infinity of n plus 1 times x minus 1. And note that we're considering what happens as n approaches infinity. Well, as n approaches infinity here, we technically have infinity multiplied by x minus 1, which, for most values of x, is going to go to infinity. This is at least true for all non-zero values of, in this case, x minus 1. If x minus 1 equals 0, then we just have the limit of 0, which is 0 itself. And this x minus 1 will equal 0 when x equals 1. And you can even see that looking at the original summation. If x is 1 here, this is the sum of 0 as n goes from 0 to infinity, which is going to equal 0. That's convergent. But that's the only value. If x is any other number, this is going to go to infinity. If x is 2, 2 minus 1 is 1, times infinity is infinity. And note that it's in an absolute value as well, which is going to also take care of negative values. So if x is negative 3, minus 1 is negative 4, times infinity is negative infinity, but the absolute value makes it positive. The only value that is convergent here is if x is equal to 1. So we have that by the ratio test, this is convergent only if x equals 1. So we had two different conclusions so far for example 1 and 2. One was all values of x make this convergent, whereas 2, we only had a single value of x that makes this series convergent. How about number 3? So we could have all numbers, we could have one number. Let's see what else we could have. We have x to the n over n plus 1 to the times 2 to the n. Again, we see x to the n that identifies as a power series. We're going to address it as such, and we're going to find the limits. N approaches infinity. First, I plug in n plus 1, so I'll get x to the n plus 1 divided by n plus 1 on the bottom is n plus 2 times 2 to the n plus 1. and then the reciprocal of my original. So I'll have n plus 1 times 2 to the n over x to the n. The easiest way to always evaluate these is to combine things into different fractions. So if I put all the x's together, x to the n plus 1 over x to the n. If I put all the n terms by themselves, we have n plus 1 divided by n plus 2. And then the 2's, 2 to the n over 2 to the n plus 1. And then considering what's happening to each of these. X to the n plus 1 over x to the n will cancel out all the values up to the exponent of n, and we just have 1 left over. So we have x left over there. Then n plus 1 over n plus 2, that will stay. We can keep it as that. And we're going to be able to analyze that using the leading term test for that limit. And then for 2 to the n over 2 to the n plus 1, again, we'll reduce that larger exponent by n, and we just have 1 over 2. If n approaches infinity, this is going to 1. So overall, what we have is x times 1/2 in an absolute value. So we have x over 2, or just absolute value of x divided by 2, because absolute value of 2 is 2. Now this one we know that this converges if the absolute value of x divided by 2 is less than 1, which we should be able to solve. If we just multiply both sides by 2, we get the absolute value of x is less than 2. So now it looks like we actually have a region or an interval of convergence. However, we're not necessarily done. What we want to consider as well is what happens if x is either of those bounds. Remember that it would be technically inconclusive if this limit came out to be 1. Well, if x was 2, then 2 over 2 is 1. That would be an inconclusive limit. If x was negative 2, we'd also have that same problem. So we have to also consider what would happen if x is either equal to 2 or negative 2, either bounds on this interval. So let's see what happens if x is equal to 2. Alright, well, if x equals 2, then what we have in my original summation, I have 2 to the n over n plus 1 times 2 to the n. That will just cancel those out. And we have 1 over n plus 1. This 1 over n, this is comparable. In this case, you would want to compare it to the using the limit comparison test. But this is comparable to the harmonic series. So this, we know, is going to be divergent because the harmonic series diverges. Well, what if x is equal to negative 2? Then we have the summation of negative 2 to the n over n plus 1 times 2 to the n. That will be the same summation of n plus 1 on the bottom, but that negative 1 to the n power will stick around, because that's not getting canceled out by anything. This is the alternating harmonic series. This is convergent, because it's the alternating harmonic series. Even if you change the bounds from 0 to infinity instead to 1 to infinity, that would actually get rid of this plus 1 here. So you actually do get the direct harmonic series. So we know it's convergent for x is equal to negative 2, and we know it's divergent for x is equal to 2. So we then say that this is convergent for x being between negative 2 and 2, but also if x is equal to negative 2. So this would be our convergence set. The set of values where it is considered to be convergent. Alright, so we've shown 3 different examples that have resulted in 3 different convergence sets. Either all values, a single value, or an interval of values. Those are the three different possibilities that you're going to get from this. You're never really necessarily going to get that it's divergent for a power series. The reason being is that you can also always have 0. And if x is equal to 0, or the power series makes it to be equal to 0, then it's convergent there. So you'll always have that it's convergent at least at one point. The question is if it is convergent elsewhere. In general, a general power series has the following form, where we also talk about its radius of convergence r. The power series for a variable x has the form of Cn times x minus x0 to the n power. Note that this is basically the same thing. The only thing that we introduce is sometimes x is adjusted a bit. We had an example of that earlier where we had x minus 1 to the n power. So, in general, you have that. And if you have that x0 power, or x to, sub-0 part, that's going to kind of shift over where you start to make your radius of convergence. Instead of being centered at 0, sometimes, like in the previous one, centered at 0 from -2 to 2, if it's at x minus x sub 0, that's going to shift over the center, just like it would for any equation manipulation. This series is considered convergent under one of the following conditions, and it's up to us to find which one. It's either convergent only when x is equal to a single point, and that point being x sub 0. We would say then that the radius of convergence r is equal to 0, because there is no radius, it's just a singular point. If it's convergent elsewhere, we say that it's convergent within an interval of x minus x sub 0 is less than r. We had that in the third example above, where we had the absolute value of x was less than 2. We would consider 2 to be the radius of convergence, how wide the interval is. Now that could also include one or both of the endpoints, so you do want to check each of those just like we did in the previous example. Lastly, you could theoretically also have it convergent for all real values of x, which we did have in the first example above. We would then say that the radius of convergence is infinite itself, that there is no defined radius, it covers all values that are in the real number set. With this in mind, we can have a little bit of a better idea of what's going to happen here when we evaluate the next few examples. Okay. Now I just had to adjust example 4 because I accidentally had one of the previous examples there. On your notes sheet, it should already have this example though. The sum from 0 to infinity of x minus 1 to the n power over n plus 1 squared. Now again, we recognize this as a power series. It's x to the n power. That's all that we're looking for. And we should be able to evaluate this using the ratio test. We also note that because it says x minus 1, that implies that the center for the radius is going to get shifted over. Remember that we'd either have the radius or the convergence set to be at that point, surrounding that point, or going to infinity. So in this case, it's going to be it's going to be at the point of 1, or it's going to be surrounding that point. Just up to us to determine that. If we do the ratio test by doing the limit as n approaches infinity, we have first, if we plug in n plus 1, we have x minus 1 to the n plus 1 over n plus 2 squared times the reciprocal of the original. X minus 1 to the n power. Rearrange the terms to pseudo combine like terms, more or less. N plus 1 on top and n plus 2 on the bottom, each of those squared. Should be able to evaluate what each of these are doing. The first one, x minus 1 to the n plus 1 power and x minus 1 to the n power. That's simply just going to take away a power of n from the top here. So we're just going to have x minus 1 to the 1 power left over. So we have x minus 1. And then n plus 1 squared and n plus 2 squared by the leading term test, because they have the same highest degree on top. We just take the coefficients, 1 and 1, And we know that this is going to converge to 1. So that's going to go to times 1. And therefore, we just have the absolute value of x minus 1, which is convergent so long as that is less than 1. Okay. In this case, if we need to identify the radius of convergence, note that we already have the absolute value by itself. There's no division or multiplication happening to it. So we would thus say that the radius of convergence is 1. That's how wide the interval will spread. If we want to find the interval itself, we can solve for x by saying, all right, well, absolute value of x minus 1 less than 1. That means x minus 1 is between negative 1 and 1. And if we add 1 to all sides, we get 0 less than x less than 2. Note that the radius is still 1. It's centered at the value of x equals 1, and it goes up 1 and down 1. So the radius itself is also 1. There's no change on that. However, our question is now, because this is not the end answer, what happens when x is either equal to 0 or x is equal to 2? So we have to check that. So x equal to 0. We look at our original summation. We plug in 0 for that. What we get is the sum of negative 1 to the n power over n plus 1 squared. This is an alternating p series of n plus 1 squared. And even if it wasn't alternating, n plus 1 squared we know converges anyway. So we know that this absolutely converges. So this absolutely converges by the absolute convergence test. And the comparison test. Because it technically is going to be smaller than 1 over n squared. If x is equal to, in this case, 2 rather, we each have the summation of 2 minus 1 is 1 to the n power is 1 over n plus 1 squared. This we know absolutely converges by the comparison test again. That means both 0 and 2 work. So therefore, our final answer for the convergence set is 0 less than or equal to x less than or equal to 2. That would be our final answer. You always need to check the bounds if those exist. If you just have a singular point, or if you have that as convergent for all r, then you don't need to do that. Let's do one more. Sum from k is equal to 2 to infinity of negative 1 to the k plus 1 times x to the k over k natural log of k squared. Now, don't be afraid of stuff like the fact that it starts at 2 instead of 0. That really is making sure that this is defined, because natural log of 2 works, natural log of 0 doesn't, and natural log of 1 would be 0 itself. So that's all this is really doing. It doesn't really matter, again, what happens in the finite sense. It all matters about what's happening in the infinite sense. Furthermore, notice that our power part of this is x to the k power. There's no adjustment on x. So that means we know that the center point should be at x sub 0, which is in this case 0. There's no adjustment here. This is x minus x sub 0 to the k power. In this case, there's no adjustment. The center should be at 0. Our question then is going to be, is it just at one point? Is it a radius around that point? Or is it all values? To do so, we're going to evaluate the limit. So the limit is n approaches infinity. We're doing the ratio test again. Note that the ratio test is going to be the absolute value of stuff, which means that this negative 1 to the k plus 1 power is completely irrelevant. We don't care about the alternating part of this. We just care about the positive components. So x to the k plus 1, so we're doing k to infinity rather, divided by, if I put in k plus 1, I have k plus 1 times natural log of k plus 1 quantity squared. And then the reciprocal of the original. K times natural log of k squared over k to the, or x to the k power. This looks a little gross, but again, the first thing you want to do is then maneuver all pieces together with like terms. So I have x to the k plus 1 over x to the k. We probably should already know what's going to happen with that piece. And then we have just the k terms, k over k plus 1. Starting to look a lot like the previous question. But then we also have natural log of k over natural log of k plus 1, all of them squared. So I can actually put all that together and say natural log of k over natural log of k plus 1 quantity squared. Okay. So we want to think about what these are doing. So for the first one, limit of k approaching infinity for x to the k plus 1 over x to the k. You can actually take this limit out of it, really. X to the k plus 1 over x to the k. Well, we're going to subtract away k from that top power. That's how we can eliminate that. And so all we have left with is just a singular x power, or x to the 1 power. K over k plus 1, that's relatively simple. By the leading term test, this is going to go to 1. And then for the third piece, natural log of k over natural log of k plus 1, this is also technically the leading term test, although you may need to do L'Hopital's on the inside if you want to. If you do L'Hopital's on the inside of that, what you would end up with is the fact that k and k plus 1 will switch places. L'Hopital's of that would result in k plus 1 over k inside of a square, because you can move the limits inside of that power of 2. And this we know also goes to 1, to the second power, which is 1. So this goes to 1 quantity squared. So this is just the absolute value of x then. And by the ratio test, this converges if that's less than 1. Therefore, we have another radius here. So we have my radius of convergence is 1 here. There's no change on it. If I had like x divided by 2, then I'd say I have to multiply by 2 and the radius becomes 2 itself. But we don't have that. We just have the x is equal to 1 for the radius. But then our question is, okay, what happens at the bounds there? So what happens if x equals 1 or x equals negative 1? Okay. If x equals 1, we can put that in, then we just eliminate that x to the k power. And what we have is the summation from 2 to infinity of negative 1 to the k plus 1 power over k times natural log of k quantity squared. Now this one may take a little bit of work to do because this one's not as direct, but since we have that negative 1 to the k plus 1 power, we should be able to think about this as an alternating series and determine if this is going to be convergent or divergent. If we do the alternating series, all we need to do is consider the limits. So the limits of 1 over k times natural log of k squared, that's definitely going to 0. So that's easy peasy. And then if we consider successive terms, 1 over k plus 1 and natural log of k plus 1 squared. If I compare that to the original, 1 over k times natural log of k quantity squared. Well, the left-hand side is always going to be bigger than the right-hand side, at least for the denominators. So because the left-hand side has a bigger denominator, it's a smaller value overall. So it is decreasing. So we have both checks. And so by the alternating series test, this converges by that test, by the alternating series test. Okay, that took a little bit of work. that means we also still need to check x is equal to -1. But this one's actually going to be kind of funny. If x is equal to -1, what we have in the original summation is that -1 to the k power times another -1 to the k plus 1 power. That just adds another k to that. So we actually have -1 to the, this would be 2k plus 1 power. Well, 2k plus 1 always defines an odd number. 2k plus 1 is always odd for all values of k. And -1 to an odd power is -1. So this is the same thing as the sum of -1, which we can actually pull outside the sum if we want to. Negative sum of 1 over k natural log of k squared. Well, this one isn't alternating now. It's just overall negative, so we need another test to solve this. There are a few different solutions. It's kind of up to you in terms of what you want to do. But the fact that I see natural log of k, that's going to hint me to maybe use integral test, although there are probably other things you can do. It's just the first one you see, go ahead and try it. If we do the integral of this, if we do the integral, we'll replace these with x's. X natural log of x quantity squared over 1, and we have dx there. That means we could set u to be natural log of x, du to be 1 over x, which we do have on the outside there. And so that just becomes the integral of du over u squared, which is -1 over u. Well, in this case, we have to have our limits here, so this is also the limit. In this case, is from 2 to infinity. So if we call that b, then that's b going to infinity. And so we actually have the limit as b approaches infinity of the result of this, which is -1 over u, right? Yeah, -1 over u from 2 to b. If we plug in these values, we plug in b and 2, we get the limit as b approaches infinity of -1 over b plus 1 over 2. This is going to go to 0 as b approaches infinity, and so we just have an answer of 1/2. That means that our series here converges by the integral test, because the integral itself converges. Therefore, it works yet again at both of the bounds 1 and -1. So we have our convergence set to be -1 less than or equal to x less than or equal to 1. Or if you want to write it as something like absolute value of x is less than or equal to 1, that also works. But that would be our convergence set there. All right, overall, these boil down to work the ratio test, see what you get, maybe check the boundaries if you have those. But that should be it for this section. What this is going to lead into is it'll allow us to actually work with specific functions. For example, arctangent is going to be an important one. This isn't necessarily in the notes, but so you start thinking about this. If you think about arctangent of x, specifically the derivative of arctangent, we know that that's 1 over 1 plus x squared. Hopefully you're familiar with that by now. If I rewrite that denominator as 1 over 1 minus -x squared, which is the exact same thing, this looks very familiar. Particularly if I say that r is equal to -x squared, 1 over 1 minus r. This is the result of a geometric series. This is the result of the geometric series of r to the n power, specifically n minus 1 from 1 to infinity. That's the result of that geometric series. And so if we defined r as -x squared, then that means we can say that the derivative of arctangent is the same as this summation from 1 to infinity of negative x squared to the n minus 1 power. Which means that we can start to define this then. We can define the derivative of arctangent instead of this fraction. We can define it instead as a polynomial of these terms of x squared. This is where this is going to be leading to, where we can start to take derivatives or just normal functions and replace them with polynomials. And polynomials are far easier to work with, both with integrals, derivatives, with differential equations, etc. So that's where we're getting to, and that's why we need to check convergence. All right. If you have any questions, feel free to put those in the comments below, or you can always ask your instructor. But with that said, I hope you have a nice day.